Hello students. So in last video we learned how to plot one-dimensional real variable function which have the integer and the fractional powers, right? In this video we are going to learn how to plot the family of ovals. So one particular case of ovals is ellipse, which you have already learnt in your 10 plus 2 courses, right? So what is the equation of ellipse that we see here? It is x square by a square plus y square by b square equal to 1. And the figure, it look like this. You draw ellipse like this, right? Where this is semi-major axis, this is semi-minor axis. This is x and y axis, right? Here you see that the power of x and the power of y both are same, and it is square, right? So you know that if something is squared, if some variable is squared, it becomes symmetric along that axis. So here we have already done x square and y square, then the curve will be symmetric in along x axis and as well as along y axis. Fine. So it is clear that since the power is even power, if something is, you already know the even function, odd function, right? So here power, since x is squared and y is squared, so both are here, this curve become symmetric along x axis as well as y axis. And also one thing is to note is that the power on the both variable is same. Hence the symmetric nature along x axis is same as it is along y-axis. So if we change this power and you will see what I mean to say. So let me generalize the equation first. So the general equation of ovals I will write like this: x by a to the power alpha plus y by b to the power beta equal to 1. So if I write this equation, okay, so if here beta is greater than 1 and alpha is less than 1, then how it will look like, let me tell you. So this will look like, since alpha is less than 1, then it will be, and beta is greater than 1. So alpha is less than 1, then this will look like something this, and so this is x-axis and this is y-axis. Fine. So this is A and this is B. So this curve look like this. And if you change this, alpha makes greater than 1 and beta you make it less than 1, then this will become like this. So this is first combination and this is second combination. So this is for second and this is for one. So how I plotted these things, I will tell you in some time later in the further course how I plotted this. So I'm just giving you an idea how the curve look like, right? So this is for first combination. What if you make alpha beta equal to 1? So I, I was earlier saying that here, uh, that since here we have already applied the modulus over x and y, that's why this become symmetric along x-axis as well as y-axis. But since the power is different on both x and y, one, so alpha is the power of x and y, beta is the power of y. Since power is different, then that's why what we see here is that the symmetric nature along x-axis is not same as along y-axis. So if you pick the curve number 1, the blue one, so if you pick the curve along blue one, so curve number 1, how it look like along x-axis, you see that its symmetric nature along x-axis is different. It is soft when it is crossing the x-axis. See here, right? It is short when it is crossing the x-axis. But when it is crossing the y-axis, it is not soft. It is well sharp. It is making cusp. So you see here, it is making cusp. So it is symmetric along x-axis. It is symmetric along y-axis. But the symmetric nature along x-axis and y-axis are not same. Both are different because we have chosen here the value of the alpha beta different. If we make the value of alpha and beta same, then the symmetric nature will be same along x-axis as well as y-axis also. But this is symmetric because we have already put the modulus over x and y, right? So let me make alpha equals to beta. Then this oval will look like, so if you make alpha equals to beta and both are less than 1, then it will become like this. It will become like this, this, where this is a x-axis, y-axis, this is b. If you make alpha and beta, so this is third combination. So this is for 3. Fine. If you make alpha equal to beta greater than 1, in this case, it will become soft along y-axis as well as x-axis. If it cross y-axis, it will be very soft and it will cross perpendicularly to the axis, whichever axis it crosses. So it will like this. It will not make cusp this time because here the value of alpha and beta is greater than 1. So how we are ensuring that the nature of curve will be like this, that those points which I told in the previous video, with the help of those points, the 8 points which I told in the last video, with those points you can plot these graphs. So we will do some examples on those points, how to plot some examples. We will do some numerical. So how to plot the graph using those points. But here the some important things I'm telling you about the family of ovals. So my bad art, I'm not able to plot this, right? So this is combination number 4. This is for 4. Fine. If alpha equal to beta equals to 1, then the curve will look like this. A straight line, because if you the alpha beta are the powers, and if you make the power 1, then it is a linear graph. You already know the equation of straight line, y is equals to mx plus c, where the power of x and y is 1. So this will make straight lines. So now you see here the power 1 is a power 1 is a separation between the two family of curves. One family of curve where alpha beta is less than 1, and one family of curve where the alpha beta is greater than 1. So alpha beta is less than 1, then the fractional power, and alpha beta is greater than 1. If you take, it is value of alpha 1, 2, 3. Those are the integer powers. So this look like this behavior is exactly same as you saw in the previous video, where we plot the power of x, where you took fractional power of x and the integer power of x, and there you saw that the integer power 1 was the separating line between the two. Here the same case, right? Yeah. One point is to be noted here: as alpha equal to beta tends to infinity, what will happen? And as alpha comma, so what will happen if alpha tends to infinity? In that case, so here you see that as alpha increases from 1 to greater than 1, the curve expands on xy plane, and it will keep on expanding but keep fixed those points where it intersect the axis, like this point, this point. So this point will be fixed because a and b are fixed, and if you keep increasing the value of alpha and beta, so this curve will getting expanding and expanding. So, so finally, if alpha and beta are very large, the curve will become a rectangle which will pass through these intersection points. Sorry, yaar. Okay. So this blue one is for alpha beta tends to infinity. So this is the family of ovals, right? This is a particular where alpha and beta are equal. If alpha beta are not equal, it will look like this, this figure. This figure is when alpha and beta are not equal. And I already told you, since we have applied the modulus, that's why it is symmetric along x-axis and y-axis. And the symmetric nature of this curve along x-axis, whether it will be same along the y-axis or not, it depends on the value of the alpha and beta. If the value of alpha beta are same, then the symmetric nature along x-axis as well as y-axis is same. If it is not same, then we will see this kind of graph, the first one, right? Now let us, how we plotted this graph. Let us think about that. So we will start from the first equation when first special case when alpha and beta are equal to 1. Suppose one first special case when alpha equal to beta equal to 1, then equation look like this. And as you know, here we have applied the modulus. Then it, so if we have applied the modulus, it is symmetric along x-axis and y-axis. So why we do not we take the advantage of this? Why we check the behavior of this curve in all quadrant? If it is symmetric, check the behavior in first quadrant, and that behavior will be similar into the all quadrant. So we will just get the we will do the investigation only in the first quadrant, and if you know the first quadrant what is the behavior of this curve, that will be the similar behavior in all quadrant. So we are not going to investigate all quadrants, right? So we'll just take only first quadrant. So this is x-axis and this is y-axis, and this one is the first quadrant. Fine. So we'll do just investigation in this. Since here the power of x and y are 1, it means that it is a straight line. Fine. And in the first quadrant, we already know that x and y are the positive. So why just write this equation in the first quadrant? In first quadrant, this equation will look like this. Fine. So you can arrange this equation, and after arranging this equation, you will see write it like write this equation in the form of y equals to mx plus c. So if you do so, just multiply by b and arrange the equation, it will look like 1 minus b by a x. Fine. So this equation will look like this, where you multiplied by b, so this is b. Okay, yeah. So here the value of c we are getting is b, and value of m is minus b by a. So it is clear that where in this equation the c is the intersection on the y-axis, m is the slope. So here we see that the slope is minus m by b, which is the negative slope because a and b are positive, and the intersection on y-axis is b. Fine. So this line intersect on the point b on y-axis at a point b. So this is y equals to b. It intersect at this point. The slope is negative. This means that it is making an angle of greater than 90 degree with the x-axis. So it will look like this. So this angle is greater than 90 degree. So this theta is greater than pi by 2. So this line pass like this, and this is the angle. So it's the slope of this line is m equals to minus b by a. So we saw here that this equation look like this. Fine. Now it I don't know what at what point this equation intersect at a. Let us check about that. So if we want to check where this line intersect on the x-axis, to know that we will put y equals to 0, because on x-axis everywhere the coordinate y is 0. Fine. So if you do so, you will see y equals to 0. Then this equation will become like this: y equals to b minus b by a x, where then this will become x equals to a. Fine. It means that this point x equals to a. Now we got the equation in the first quadrant. Fine. We know the slope. We know that it is a straight line. We know that at at x-axis where it cut, at y-axis at where it is cutting. Now, since we know the behavior of modulus, we will make it its mirror image in all the quadrant. So in all quadrant, it will look like this. Why this is looking like this? Because we have already applied the model. That's why it is symmetric along x-axis and y-axis, and power on both x and y are same. It is that's why it is the symmetric nature is also same along x and y-axis. So this is a case when alpha and beta are equal to 1. Similarly, you can plot it for the ellipse when the power alpha and beta are equal to 2. Similarly, you can plot that. Okay. So I think you got the flavor of family of ovals, how this family look like, when alpha beta are same, when alpha beta are not same, what is the separation power, which is alpha and beta equals to 1, which separate the two kinds of family, one integer power family and one when alpha is less than 1, when alpha is greater than 1. Fine. So in the next video, you will see how to plot the family of spirals. Fine. So since this video is becoming a bit longer, so in the next video I will tell how to plot family of spirals. Thank you.